Hello everyone, welcome to the Spectral Geometry in the Cloud seminar. Today we have the pleasure of having Alexei Stepanenko, who will speak about computing eigenvalues of the Laplacian on rough domains. Alexei, the stage is yours.
Thank you very much. Thank you for the invitation. I'm very happy to speak here. So I'm going to talk about today a recent preprint, which I wrote in collaboration with Frank Rossler, who's also at Cardiff University. And the topic of the preprint is the computability and non-computability of eigenvalues of a Dirichlet Laplace operator on rough domains and associated functional space results. Okay, so throughout the talk, I'm going to consider Dirichlet Laplace operator on bounded planar domains. So I'm always going to consider dimension equal to 2. So by Friedrich's extension, we can define this operator on any bounded domains. We don't need any clarity assumptions on the boundary to define the operator as a positive self-adjoint operator. Okay, so I'm going to denote the spectrum like this, and I'm often going to talk about the spectrum of a domain referring to the spectrum of a Dirichlet Laplace operator, because I'm always going to talk about a Dirichlet Laplace operator. Similarly, when I talk about the eigenvalues of a domain, I'll always mean the eigenvalues of a Dirichlet Laplace operator on that domain. Now it's quite easy to see that by Relic's theorem that the spectrum is discrete. So it consists entirely of eigenvalues of finite multiplicity, which are positive, and which satisfy this asymptote. They go to infinity as k goes to infinity. Okay, so there are several nice classes of domains that people often consider. So one is a class of domains whose boundary is locally the graph of a C2 function, twice continuously differentiable. And another nice class is that of polygonal domains. So that's where the boundary is the union of line segments. And for these nice class of domains, we have some nice spectral properties. For instance, if UK denotes the eigenfunctions, C2 boundary ensures that the eigenfunctions live in H2. When the polygonal, when you have a domain with a polygonal boundary, this isn't always true. If you have a re-entrant corner of a type drawn here, but still the eigenfunctions live in HS for some S strictly greater than 1, and it depends on this the angle of the re-entrant corners. What's also been known for many years is that there exists robust and importantly convergent numerical methods for computing the eigenvalues of domains in this class. But in general, bounded domains can be much, much wilder than this. They can have, for instance, fractal boundaries, like this Cox snowflake. The interior of this Cox snowflake has a fractal boundary, and the interior of this Phil-Julia set is another example of a domain with a fractal boundary. The boundary, even if it's connected, it may not be locally connected. For instance, like the interior of this Warsaw circle. And you can even have a situation where the boundary has a positive area. So an example is the interior of this Osgood curve. And the question we want to ask is, when we consider a larger class of domains, which includes some of these guys, can we still compute the eigenvalues? Does there still exist convergent numerical methods? And in other words, what we kind of want to ask is, at what point does numerical computation break down due to boundary regularity? This is a slightly ill-posed and ambitious question, maybe. However, we can formulate this all rigorously in the language of solvability complexity indices, which I'll present in the next part of the talk. After that, we're going to see that there'll arise some function space problems to do with approximating some of these rough domains by more by nicer domains, for instance, polygonal domains, and that's what I'll talk about in the second half of the talk. Okay, so first I'll talk about the computability results. Okay, so throughout the talk, S0 is going to denote the class of bounded domains. And I'm going to consider subclasses of bounded domains, which I'll denote by curly S. And we're going to allow S to also be S0 at some points. And our aim is to construct a computer algorithm that's able to compute the spectra of any domain in a fixed class, where we're going to try and make this class S as big as possible, right? So there's a single computer algorithm which has to be able to compute the spectra of every single domain in the class, right? So now I have to make more precise what I mean by a computer algorithm. And I'm going to make a couple of assumptions, which may or may not hold in reality, but are useful assumptions to make for the simplify the analysis and get going with some proofs. Right. So first of all, for any points in X, so for any point X in the plane, the computer algorithm has to be able to determine whether or not that point lies in a domain or not. And this is quite clear because in order to compute the spectra, the domain has to know what the domain looks like, and that's why it has to know which points lie in it. And secondly, the computer algorithm has to be able to perform arithmetic operations and comparisons on real numbers. So in reality, computers can only do floating point arithmetic, but it's useful just for simplification to assume that they can do real number arithmetic as well. Okay, and with this, we can define a type of computer algorithm, which we call an arithmetic algorithm. And what an arithmetic algorithm is, formally is a map from a given fixed class of domains to a closed subset of R, such that the output, right, the output is going to somehow approximate the spectrum of O for any given O. The output is obtained by a finite number of arithmetic operations on a finite input set. And what the finite input set is nothing other than the information of whether a given finite number of points, x1 to xn, they lie in O or not. Okay, so this indicator function, chi O x1, for instance, will be equal to 1 if x1 lies in O and 0 otherwise. So that's what we mean by a computer algorithm. And a little bit of a disclaimer here. Technically, these points, xj, may depend on O, since the algorithm, we allow it to be adaptive. That is, the algorithm, it can test a bunch of points, do some computation, and based on those computation, it can decide to test some other points. And so technically, we require some additional consistency hypotheses. However, please don't worry too much about this because it's not going to play a huge role in today's talk. Okay, and so the output of this an arithmetic algorithm is supposed to approximate the spectrum of a domain, of a Dirichlet-Laplace operator on a domain. And in order to measure how well it approximates the spectrum, we use the Touch-Wets distance for unbounded Euclidean sets. These sets AB, in our case, they'll be possibly unbounded subsets of R. So the definition looks a little bit complicated. However, what you need to know is that the Touch-Wets distance is, if you don't know about this thing already, all you need to know is that it's essentially a generalization of the Hausdorff distance, in the sense that for A and B, for sets A and B which are bounded, the Touch-Wets distance is equivalent to the Hausdorff distance. Okay, and a nice property tool to know about is that when we're considering the Touch-Wets distance between the spectrum of some domains, say a domain O and ON, a sequence of domains ON, you have a convergence of the spectrum with respect to their Tooch-Wetz distance if and only if every single eigenvalue converges also. So this is with respect to counter multiplicities. Right, so the spectrum converges with respect to Tooch-Wetz distance if and only if the eigenvalues converge. And so now we can rigorously say what is a convergent numerical method. Well, that is none other than a sequence of arithmetic algorithms on whatever class of domains. Class of domains S we're considering, which for every single domain in that class converge with respect to their Tooch-Wetz distance. And with this, we can say stuff about computability and also non-computability. So this is our first result, which I want to present. So now we consider the entire class of bounded domains. And what we can prove is that there does not exist a sequence of arithmetic algorithms on this on the class of bounded domains such that it converges for every single domain, for every single bounded domain. Okay, so there doesn't exist a numerical method which is able to compute the spectrum of an arbitrary bounded domain. And the idea here is we construct a counterexample, and that counterexample, say, you fix a sequence of arithmetic algorithms gamma n, and what you can do for that gamma n, you can construct a pair of domains which the algorithm it can't distinguish, right? Where based on the points, it's the countably infinite number of points it's sampled, but the spectrum is very different. Okay, so this is using the fact that arbitrary bounded domains can be pretty wild. Okay, so we've proven that there can't exist a numerical algorithm capable of computing the eigenvalues of an arbitrary bounded domain, but can we consider maybe a slightly smaller class of bounded domains, but still including some interesting fractal guys, for which there does exist a convergent numerical method. And for this is the contents of our the next result that I want to present. And the class we consider is S1. So S1 is any bounded domain satisfying these four conditions. First of all, I'm going to go through them one by one, right? So first of all, we require that a domain is topologically regular. That is, it is equal to the interior of its closure. So if you look at the domain depicted in figure A, it's a crack domain, right? So you have a domain and you take out like a line or a little crack. When you take the closure of this domain, the crack goes away. And when you take the interior, again, you don't recover the crack. So this type of domain is not allowed. Second of all, we require that the area of the boundary, i.e. the two-dimensional Lebesgue measure, vanishes. It's equal to 0. So domains like the interior of the Osgood curve, we don't allow. Now, the third condition, so here, this hash C, using this notation to denote the number of connected components. What this is essentially saying is that the domain has a finite number of holes, and they're all well separated from each other, as well as separated from the outer boundary of a domain. So to understand this, you can look at the domain depicted in figure B. And this domain, the complement of it. So these two holes are touching, right? So therefore the complement of this domain has 2 connected components, whereas the interior of the complement has 3 connected components. And the final condition is more technical in nature. We'll see this quantity appearing again, Q. And it's basically saying Q is defined as the infimum over the diameter of all the path connected components, and that's we assume that's positive. So with assumption 3, the boundary can only have a finite number of connected components anyway. However, if you have singularities of a type we saw from the Warsaw circle, if you have crazy singularities, a given connected component of the boundary can have more than one path connected component. And in fact, there's no reason that I can think of why it shouldn't have a given connected component of the boundary can have an infinite number of path connected components. And actually that's okay for us. However, in this case, we require that the diameter of the path connected components is bounded below uniformly. And I don't know whether such a domain exists. Okay, but anyway, for any domain in this class S1, now we've defined this class S1, what we can say is that there exists a sequence of arithmetic algorithms on the class of domains S1, which for every single domain in the class S1 converges with respect to their Touch weights distance. And throughout the rest of the talk, whenever I refer to gamma n, I'm going to refer to this gamma n, the gamma n of this theorem. Okay, so to understand better this class S1, let's look at some examples. So recall that a Jordan curve is the image of any continuous injective map of a circle into the plane. So in other words, it's any closed non-intersecting path in the plane. And it's quite easy to show that the interior of any Jordan curve of zero area lies in our admissible class S1. So for instance, the Cox snowflake and the field Julius set, or the boundary of the field Julius set is the Julius set itself. These are Jordan curves of zero area. Okay, so you have to be more precise about which class of Julius sets you can consider, because you can have all sorts of stuff. But for an interesting class of Julius sets, you can prove that the Julius set is a Jordan curve of zero area, and therefore it lies in class S1. So the interior of the Warsaw circle actually isn't a Jordan curve, because it's not path connected. The boundary isn't path connected. However, it still lies in our class S1. The interior of the Osgood curve, however, has a boundary of positive area, and therefore it doesn't lie in the class S1. We can't deal with this person, or this domain. Sorry. Okay. So how do we consider? How do we construct the algorithms gamma n? Okay, so the gamma n are constructed with two stages of approximation. Okay, so the first stage is to get the domain, which is very rough, and approximate it by a polygonal domain. And the second stage is to just apply the finite element method to the polygonal domain. Okay, and what we're really going to be worried about is the first stage. Let me be more precise. The first stage of approximation is to take your O and construct pixelation, what we call a pixelation approximation of O. So what is this? You take a grid spaced 1 over n, and then you look at all the points in the grid, and you record which points of that grid lie inside the domain. And the grid points which lie inside the domain, we don't know this by Ln. And to construct the pixelated domain is simply the union of 1 over n sized boxes around these grid points in Ln. And then we take the interior of this union just to ensure that the domain is open, right? So the pixelated pixelation construction is indeed a domain. So it's just as in the picture. And the nice thing about pixelated domains is that if you know anything about the finite element method, you need a mesh, you need a triangulation of a domain, and this is super easy to construct a mesh from a pixelation approximation. Okay, there's just a union of boxes. So you take each box and you chop it in half into two triangles, and you have a mesh right there. And so therefore, we can easily apply the finite element method. So I mentioned before that there exists robust numerical methods for polygonal domains. So these are been developed to a very, very high level, to the point where you can give me you can give me a polygonal domain, and you say, I want the answer to within 0.001 accuracy with respect to Tooch-Wet's distance. And these guys that have methods which will produce a numerical answer for you, which you know is within that error which you've specified. And you can do this with mesh refinement and computable error bounds, but it's not there's many different things you can do. Actually, it's basically you can compute the polygonal domain, the eigenvalues of a polygonal domain very easily. And we encode this with the following lemma. There exists an arithmetic algorithm on the class of pixelated domains, such that the arithmetic algorithm achieves, for any given pixelated domain, achieves an error 1 over n with respect to the Tooch-Wet's distance. And formally, okay, finally, we define our algorithm gamma n like this. So it's just simply the finite element approximation of the pixelated domain. Okay, so now we're going to try and prove convergence of this sequence of arithmetic algorithms. So written out the definition in the first line, and then you can apply the triangle inequality for the Tooch-Wet's distance and separate the finite element error and the geometric approximation error. The finite element error, as shown, is just is equal to is less than 1 over n, because we've done all this mesh refinement and all of this. And this will, of course, tend to 0. So all that's left is we need to show that the spectrum of the pixelated domains converges with respect to their Tooch-Wet's distance. And as we've shown, well, not shown, as we've mentioned, this is basically the same thing as saying that the eigenvalues of the pixelated domains converge, right? For every domain in this class S1 that we've considered, in this class of rough domains, admissible rough domains. And showing this is going to be the topic of the remainder of the talk, and this is going to motivate some Moscow convergence results. How am I doing for time? Okay. Yeah, and just to mention the type of, well, first of all, the formalism of arithmetic algorithms that I've presented today is all coming from the theory of solvability complexity indices. And in particular, the computability results that I've presented are an example of what's called a delta 2 classification here. And there's many different types of classification, actually. So you can, there's more finer types and higher types. And if you're interested in this kind of thing, I recommend checking out these papers. Okay, so now I'm going to talk about some more functional space, function space results, in particular Moscow convergence. I'm going to talk about a type of Poincare type of inequality. So Moscow convergence. So for people considering differential operators on rough domains, quite a standard tool is Moscow convergence of subsets of Hilbert and Banach spaces. And what we're going to consider is the Moscow convergence of the H10 Sobolev spaces, right? So this is a notion of convergence for Sobolev spaces, for the H10 Sobolev spaces themselves. So consider a domain O and a sequence of well, actually, it's any open set you can define this for. Consider an open set O and a sequence of open sets ON. And you have Moscow convergence for the, I'll often say we have Moscow convergence of ON to O. But really, this is Moscow convergence of H10 ON to H1 of O if these two conditions hold. Right, and the first condition is saying, okay, so if you have a function in your limit domain in H10 of O, then there has to exist an approximating sequence of functions UN, which each lie which are on ON, the line H10 of ON, which converge in H1 norm. And secondly, we have like a weak convergence condition, which we require. So say we have now just a subsequence of these domains, O and J, and consider any functions uj in H10 of O and J, right? Which converge weakly in H1 to some function u. This holds. We have to be able to know that u is in H10 of O. That's the second condition. And so Moscow convergence is really useful because at least when the domains are bounded, they imply the convergence of eigenvalues of a Dirichlet Laplace operator, which is what we're interested in. And you also get other interesting convergence results, for instance, for the Poisson equation, the Heath equation, and other things too. So in particular, this lemma holds if we have a sequence of bounded domains ON and a limit domain O. Then Moscow convergence implies convergence of eigenvalues of a Dirichlet Laplace operator. Right. So now let me go through some known results about Moscow convergence. So the first thing to know about Moscow convergence is that if you're able to approximate your domain from below, like from within, so in other words, if you have a domain O and a sequence of nested approximations, that is, they're nested in the sense that ON is contained inside ON plus 1, and these are all contained inside of O, and the union of ON is exactly equal to O, then we automatically have Moscow convergence for the sequence of domains ON to O. Okay, but the problem with this is pixelated domains are not subsets of the domain, and in fact, it's impossible when you consider rough domains. It's impossible to construct approximations of those rough domains which are nested purely based off just pointing of picking individual points, right? And that's just because the rough domains can be contorted. They can just go in between all the points you've sampled, and so you can never do this. And so we need to consider approximations which are not nested. And okay, so it turns out if you can approximate from the inside and approximate from the outside, then you're okay, right? So let me present some results for approximations from the outside. So you can define another H10 space like this. So you can define, this is defined as H1 functions U, which are equal to 0 almost everywhere outside of the domain, and we call a domain stable if the H10 space that we consider is equal to this other definition. And there are examples of non-stable domains. And McLean, in his book, you can find a proof that if the boundary of a domain is locally the graph of a continuous function, then that domain is automatically stable. right? But for instance, this is not so useful for us because even the Koch snowflake, it's not the graph. It's not locally the graph of a continuous function. Fractal domains, they don't satisfy this. Okay, and the reason why stability is useful is if you have an approximation from the outside for a stable domain, then you have Moscow convergence. And in fact, if you have any, it really follows from this that if you have any kind of for a stable domain, you have any sequence of domains which converge geometrically in any sort of nice enough sense, then you'll have Moscow convergence. So recently there's been a few nice results about Moscow convergence. So the first one here is Hinz, Rosanova, Pierre, and Tiplev. And they're motivated by shape optimization. They consider a different type of Moscow convergence that's useful for Laplace operators with different boundary conditions, for example, Rabin boundary conditions. And they prove Moscow convergence for epsilon infinity uniform domains, which actually includes some fractal domains as well. One I want to mention here is a result by these authors. David Hewitt actually gave a talk at the Cardiff analysis seminar just earlier. And they prove stability for a range of other Sobolev spaces as well, HS Sobolev spaces for domains which are so-called fat in the Trebel sense. Okay, so what we wanted to do is consider our results are in some sense more restrictive than these, and in some sense they're wider. They're more restrictive because we only consider H10 Sobolev spaces, but accordingly this gives us some more freedom, and we can consider wider, or more or less wider class of domains which are much more topological in nature, right? And we can include some crazier domains. Okay, so just to recall, before in that computability result, we showed that in order to prove convergence of our sequence of arithmetic algorithms gamma n, we need the eigenvalues of the pixelated domains to converge. Well, now what we've reduced this down to is shown that the pixelated domains converge in the Moscow sense, right, for every domain in our admissible class S1. Okay, and so what this was our aim, but when we proved this, we realized actually we got a more general result, which works not only for pixelated domains, but for a wide range of other approximations. Okay, so recall that DH denotes a Hausdorff distance, and we're going to consider any domain O in the class S of admissible domains S1 I defined earlier. For instance, the interior of any Jordan curve of zero area. And then I'm going to consider a sequence of domains On, which are all bounded, which converge geometrically in the sense A. Right, so we assume that On converges to O in the Hausdorff distance, and also that the boundaries of On converge to the boundary of O with respect to the Hausdorff distance. We assume that the boundary of On are locally connected for each n, so this is quite a weak assumption for us, because we're going to consider On which are polygonal. Certainly, polygonal domains have locally connected boundaries. And if this holds, then we have Moscow convergence. This is our Moscow convergence result, and I would say this is our main technical result. It's most of the effort that goes in the proofs in the paper goes towards proving this. And okay, let's first apply this to pixelated domains and show that this really does imply the computability result. In order to do this, we need to show that the pixelated domains converge in the sense of the Moscow convergence theorem. And we can show this. It's a little bit of effort, but we can prove it that if O is topologically regular, bounded domain with a boundary which has 0 area, then the pixelated domains converge in the sense of our Moscow convergence result, in the sense that our Moscow convergence result requires, right? So in this sense. And so therefore, the Moscow convergence result, in effect, it allows us to prove the computability result theorem 2. It allows us to prove convergence of this sequence of arithmetic algorithms gamma. Okay, so now for the rest of the talk, we're gonna talk about the proof and results arriving in the proof of the Moscow convergence result. And so before I move on, I just mention another quite interesting application of the Moscow convergence result. So you can see the Koch snowflake here, and you can see it's pixelation approximation. But there's also another very natural way to approximate the Koch snowflake, which just arises from its construction. So if you're not familiar, the way you construct the Koch snowflake is you start with a triangle, and then you add 3 smaller triangles, and then you continue like this. You add many more smaller triangles around the outside, and more and more smaller triangles, and you end up with this kind of domain. Well, this process it yields a sequence of polygonal approximations, which we call the prefractal approximations, and these also often these also naturally satisfy this kind of a geometric convergence condition that is required by a Moscow convergence result. Okay, and so when we set about proving this Moscow convergence result, it turns out we needed to prove Poincare-type inequality, and we think it's of independent interest. So I'm gonna present it here. So this is a Poincare-type inequality, but it's a Poincare-type inequality for these kind of neighborhoods of the boundary, right? Which is in gray. So I'm going to call this. People have different names for this. I call it a collar neighborhood. I'm going to call this the collar neighborhood of a width R, and this is defined and use this notation, partial RO, and to be defined as the points in the domain which lie a distance strictly less than R away from the boundary of the domain. And our Poincare-type inequality, it applies to any open set O. So we don't require it to be bounded now, for which this quantity Q partial O is positive. This is what we saw. We saw this quantity before. It's the infimum of the diameters of the path-connected components. Here it holds some more meaning because, in particular, if you have a domain like, for instance, a punctured plane or any domain, and you take out one point, so you have a connected component of the boundary, a boundary component, which is a single point. Well, that connected component is going to have 0 diameter, so this wouldn't be satisfied. So this is saying you can't take a point out of your domain. You can't have like single. You can't have boundary components which are single. And then for small enough R, and you know, for R less than R naught, where R naught is defined explicitly here, we have this Poincare-type inequality. So this is kind of like the classical Poincare-type inequality. Instead of integrating on the left-hand side over the entire domain, we just integrate. We consider the L2 norm over the collar neighborhood, and on the right-hand side we have the L2 norm of the gradients of a collar neighborhood of a slightly larger width. And the constant, which is important for us, it's independent of the particular domain that you consider, and it's linear in R. So when you take R to 0, the constant is gonna go to 0 at a specific rate. Okay. So let me see how much time we have. Okay, so we have about 18 minutes. So I'm going to try and sketch the proofs, or as much of the proofs as I can. And seeing as it is the main tool that we require, I'm going to start with the Poincare-type inequality. Also, it's in my opinion, the most fun part of the proof. And before moving on to our Poincare-type inequality, I'm going to review the elementary but very nice proof of the classical Poincare inequality, which is shown down here in the boxed equation. And this is really what inspires ours. So, okay, so we consider a domain O, which is let's assume it's a bounded domain, and let's assume it's contained in a box. It's a bounded planar domain which is contained in a box of side length r. And what we do for any points in that domain, we construct a path from outside the domain into to that point. And these paths are unit speed in the sense that the magnitude of the derivative with respect to t is equal to 1. And what we can do then is, okay, so at the start of the path, okay, so we fix a function u, which is smooth, compactly supported inside of O. And at the start of the path, the points at the start of the path, the function u is equal to 0. And so therefore, we can express the value of the function u at the point P in this way, using the fundamental theorem of calculus, right? So we've integrated from a point where the function is 0 to the point P. And so this is useful because we already have an expression involving the left-hand side is function, the right-hand side has a derivative already. So we take that L2 norm, we look at the L2 norm of the function u, we stick this expression for the point values of P in here. What we can do then is we can apply Cauchy-Schwarz to this innermost integral and get this expression on the second line. And these terms little x, they're all less than r. So if we approximate this guy by r, that just brings out a constant r. And then we also approximate this integral from 0 to x by an integral from 0 to r. And we have an extra integral over x. The integrand doesn't depend on x, so we have constant of r squared. And there you go. We have the Poincare-type inequality. And by density, actually, it's okay that by density of C infinity C in H10, we get the inequality for all functions in this space. Okay, so we draw paths basically from the boundary where the function is u is 0 to the point P. So we can do the same thing. We can do the same thing for our color neighborhoods, right? So we construct what I'll call now a bundle of unit speed paths, such that the paths they start at the boundary where a function h10 is kind of 0, and they go to the point P. So gamma P, it starts at the boundary and it goes to the point P, and LP is the length of the path. Again, we fix a function u in C infinity C of O, and then we express the function, the point values of the function in this way. And it turns out if you do the same procedure as in the previous slide, exactly the same thing, Cauchy-Schwarz, then you can prove this inequality, theorem 4, which is written at the top, if the bundle of paths, gamma P, satisfies these two conditions. So the first is that okay, so the width for the color neighborhoods, right? So any point in this color neighborhood is less than a distance r away from the boundary. So you can kind of expect that the the path from which we should draw from the boundary to that point P has to be less than a constant times R. And the second condition is more difficult to understand. It's kind of almost like a mass transportation kind of thing. But what it's really saying is that the bundle of paths can't concentrate too much. And I'm going to look at some examples in the next slide, which will make this clear. Well, not necessarily make it clear, but it's which will illuminate it a bit, and it's a good way to understand. But what we do basically in our proof is we explicitly construct such a bundle of paths and gamma p satisfying these two conditions. Okay, so let's have a look at some examples of domains, their color neighborhoods, and what kind of paths you may or may not want to construct. So these examples have actually, they're not in our paper, but they've been worked out in my thesis. So these are some explicit examples, which you can do everything by hand. The first example is the case where the domain is a half plane. So you can see the domain is light blue and also dark blue as well. The color neighborhood is in dark blue, and the boundary here is the y-axis. And the way you would draw your paths, the way you would construct your paths for this domain is simply just to go horizontally in a parallel fashion as drawn here. These paths, they don't concentrate, and they are all of length less than r, and it's quite easy to show that they satisfy the conditions in the previous slide. I'm not going to go through the calculations today. Next kind of domain you can consider is a punctured plane, right? So you have R2 and you just take out a single point, let's say the origin. And what you can do is explicitly show that there doesn't exist a bundle of paths, gamma p, which satisfies the condition 2 from the previous slide. And that's because any paths which you might hope to draw, any bundle of paths which you might hope to construct, they'll always concentrate near that single boundary point which you have. And you can show that this will always cause the inequality of condition 2 in the previous slide to fail. So next kind of domain which we might want to consider is a domain with like a reentrant corner, right? So you can imagine, now you can just imagine a domain to be the whole of R2, however you take out the lower left quadrant. And let's try and draw paths to the corner parts of the column neighborhood. So the part, hopefully you can see my mouse. And the obvious way to do it would be, okay, you take a point in the corner region of this column neighborhood, and you just draw a straight line to the closest path, closest point on the boundary. And so you'll end up with paths drawn this way on the bottom left, right? This is not admitted. You can show that this bundle of paths doesn't satisfy the inequality of condition 2 of the previous slide, because the paths, they concentrate near the corner. But actually, there's a slightly cleverer way to construct the bundle of paths to this corner region, to the points in this corner region of a column neighborhood, and that's depicted in the bottom right picture here. So now you start with a longer segment of the boundary. You kind of go up and you turn the corner, and these paths, they don't concentrate. It's quite clear from the picture. They don't concentrate in any way, and so therefore they satisfy assumption 2, the condition 2 of the previous slide. However, also all their lengths are bounded by, like, they're certainly, all the lengths are bounded by 3 times r, where r is the width of the column neighborhood. So this is an admissible bundle of paths. So in general, How do we construct this? Well, I'm not going to construct everything explicitly for you today. However, hopefully I can give you a little bit of an idea. We divide R2 into non-overlapping boxes, and we're going to call them cells, right? So you just consider cells, and we pick these boxes to be exactly size R, so exactly the size of the column neighborhood we consider. And it turns out this is a useful choice, and we're going to use this cells as a kind of a structure within which we can construct all our bundle of paths. Then we pick out some of these cells, and we give them special names because of how the boundary intersects the cell. So for instance, if there exists a path-connected subset of the boundary of O, which goes from one side of a cell to the other, in the way depicted in the picture, we call that a G cell, right? And if there exists a pair of cells for which there exists a path-connected subset of the boundary, going from one long edge to the other, we call that an LG cell. And these are nice cells. These are nice because it turns out they're very good places from which to start your bundle of paths. So now let's say you just pick one cell, C0, which intersects the column neighborhood. So intersects partial RO. And well, how do we construct the paths gamma p for p in this C0 intersection between C0 and the column neighborhood? Well, first thing we do is we find a nearby G cell and LG cell, right? So it turns out we can prove if this if you remember the quantity Q partial O being positive, it turns out if this is satisfied and R is small enough, there'll always, for any given cell, there'll always exist a nearby G cell, LG cell. And then what we can do is find a sequence of other cells which go from the G cell, LG cell to our cell C0, and you can kind of draw your paths within that kind of cell path. And those paths, they won't be too long. They'll be something like bounded, like the lengths of all these paths will be bounded by something like 25 times R or something like this, if I remember correctly. And they'll never concentrate because of how they're constructed. And that's how we construct the bundle of paths. Okay, so I've got 5 minutes left, so hopefully I can give you an idea of how you can go from this Poincare inequality to Moscow convergence. And the first thing is this proposition. And what this proposition does, it reduces Moscow convergence for H10 sub-Left spaces to establishing two types of Poincare inequalities. One is inequality 1, that's exactly what we just sketched the proof for. And the other is the Poincare type inequality, except now we require that it holds uniformly over a sequence of domains ON. So let me just go through that a little bit more carefully. And I'm going to let Ln be equal to this quantity. Okay, so Ln tended to 0 is precisely the geometric condition that our Moscow convergence result requires. And we suppose that there exists a sequence epsilon n, which tends to 0, and it can tend to 0 as slowly as you like, but it has to be bounded below by 2 Ln. So in particular, this implies that Ln has to go to 0. And with this, there exists constants C alpha, which in our case, when we verify this, there'll be numerical constants, universal constants, such that these inequalities hold. Okay, and how do you prove this? We prove this using cutoff functions. So if you remember the first condition for Moscow convergence, that's for any function in h10 of O, there exists un in functions on On, which converge to U with respect to the h1 norm. So we fix U, we fix function h10 of O, and then what we do is we construct some cutoff functions. These are smooth. They're compactly supported inside of On, and we construct them in such a way that they're equal to 1 outside of the epsilon n column neighborhood of and then we define un in this way. We define un as chi n times u, and this is nice because now maybe I should have wrote that. Chi n times u, because chi n is compactly supported inside of On, chi n times u, it vanishes at the boundary of On, and therefore it lies in this space, h10 of On. And then it turns out it's some inequalities, a few inequalities that this Moscow convergence condition, the Poincare inequality 2 for the sequence of domains On, turns out this is a sufficient condition to prove that chi n u tends to u in the h1 norm. And similarly, the inequality 1 that comes in when you want to prove this the second Moscow convergence condition, the one involving weak convergence. Okay, so I'm a bit out of time, but that's okay. All I wanted to say here, it's not that important to go through all of this. In order to prove with this the first Poincare inequality for the single domain, it just follows immediately from theorem 4. In order to prove a Poincare type inequality for the sequence of domains, well, actually this follows from a geometric characterization of the boundary of On under this conditional Ln goes to 0. You can prove a geometric characterization of it, and then you can then use that geometric characterization to go from the Poincare type inequality for the single domain to the Poincare type inequality for the sequence of domains, and that's how you conclude the proof of the Moscow convergence result. Oh, thank you for listening, and welcome to answer any questions.
Thanks a lot, Alexei, for the very nice talk. And now we have time for a few questions. So if you have any questions, you can either ask them in chat or unmute yourself and ask them directly. I'll start with a question myself. So at some point you were talking about these classes of domains with this S0 that has for which there's no algorithm, and this S1 for which you have these approximating algorithms. And you had four conditions to respect to 4 conditions to satisfy to be in this S1 class. Do you have example of domains that satisfy all of these conditions except one, and for which there is no algorithm for every one of those conditions?
Oh, I would say we haven't looked at counterexamples in that detail. The one thing I would say is that okay, one thing I can talk about is that the domain, when we construct these counterexample, O1 and O2, we take like O1 to be like a square or something, and O2 is that certainly it's not topologically regular. But the answer to your question is we haven't looked at the counterexamples in that sort of detail when it comes to, especially when it comes to the non-existence of algorithms.
I mean, I think this is more now a comment than a question, but I think it would be interesting to know of these conditions which are technical and which are really fundamentally important assumptions.
I think Okay, so I think one is not technical. I think because it's not that crack domains are a problem, is that if you have like an infinite number of cracks, you can't find those infinite number of cracks just by sampling points. This much is clear. And also two is really important because say if I go back to this Osgood interior of this Osgood curve, if the boundary of domain has positive area, then it's difficult to see how you're going to, just by sampling points, find an approximate domain which approximates the area sufficiently well, right?
Yeah.
And if you don't approximate the area of the domain, then you just simply cannot expect to have good spectral approximation.
No, of course.
Yeah. The other two, 3 and 4, I do suspect that they're more technical assumptions. We leave them in there for simplicity of the proof.
All right. Do we have any other question for Alexei? All right. Well, thank you for the very nice talk, Alexei. We will